parts. In the first one, we introduce the variable order discrete neural network and investigate its stability. In the second one, we present a new 3D chaotic discrete time neural network and address its stabilization. Then we have a conclusion and some references. As known, variable order discrete neural networks are dynamical system represented by non-integer difference equation where the fractional order is a function that varies throughout discrete time. Despite the fact that dynamics of such systems are required for the effective applications, very few studies have been published on the subject, and this work makes a contribution to this topic by introducing a nonlinear nabla variable order discrete neural network and addressing its stability or asymptotic stability. Furthermore, a new chaotic discrete variable order neural network is presented, and its chaotic dynamics is stabilized using a suitable controller. Also, numerical simulations are performed in which we are going to illustrate the efficiency of the proposed theoretical method. We start with some mathematical background. We have first definition of the left nabla fractional variable order sum, which is presented in 1. Then we have the definition of the variable order capital nabla difference equation, the difference operator, which is given in 2. The next lemma provides us an important inequality and very useful, which we're going to use in our investigation and study. Now we consider this equation, which is a variable discrete equation. The equilibrium point of this system, which is called x0, is an equilibrium point if and only if condition 5 is satisfied. The last theorem is regarding the asymptotic of the considered equation. So equilibrium itself is asymptotically stable if there exists a positive decrease in diagonal function that satisfies inequalities 6 and 7, where the order in this case is a variable order function bounded by 0 and 1. Gamma 1, gamma 2, and gamma 3 are discrete class K functions. We move on to the first part of the main result, where we introduce the variable discrete neural network 8, where the used operator is the capital nabla difference operator. X represents the state vector, I is the self-fixed by connection weight matrix, B is the connection weight matrix, G is the activation function, and finally I is the vector of external inputs. Before we address the stability of the considered system, we have provided two assumptions. In the first one is regarding the activation function, which is supposed to be continuous and Lipschitz function, which means that it satisfies inequality 9. The second assumption, we suppose that there exists a negative constant D, which is defined in 10. Now, if both previously defined assumptions hold, then the system 8 is asymptotically stable. For the proof, we assume that the equilibrium point of the system is x star, which verifies equality 11, and which we're going to translate to the origin using the change of variable 12 to get the new system 13. Now, we choose the diagonal function, which you can see is a positive function defined in 14, and we're going to evaluate the variable order nabla fractional difference of this chosen diagonal function. So, by applying this operator to the chosen function, we can have equality 15, which is equivalent to equality 16 by using the lemma provided previously in the mathematical background. Then, after replacing the equations of the system and using the first assumptions regarding the activation function, we can have these three last inequalities. And after making some calculation and simplification, we can have this leads us to inequality 22. By defining the constant 24, which is negative constant, we can have that the variable order capital nabla difference of the diagonal function is negative, and this means that, according to the previous theorem, that the system is asymptotically stable. Now, to illustrate or as an application of this theorem, we have considered.
You have said that you theorem 5. Can you see theorem 5? Nonlinear operator. Theorem.
Okay, that was three.
Nonlinear operator.
Concernant
Maximum. هي رسام. نخدمو رسام. رسام ماهيش For example, we have considered two-dimensional discrete time network defined in 25, where the chosen parameter of the system and the variable order function along with the initial conditions are defined in 26 and 27. We have also provided the local solution of the system in order to perform simulations. Since we can easily check that the parameter of the system satisfies assumptions 1 and 2, and with the local solution provided, we can have this figure which shows the asymptotic stability of the system. Moving on to the second part of the main results, first we're going to present a three-dimensional continuous fraction order Hopfield neural network in 28. This network has been studied previously in the literature and have shown to have dynamical behavior for the fractional variable order function defined in 13. And based on this model, we're going to present a new model defined in 31, where you can see that the operator in hand is the variable order capital lambda difference operator, with this parameter defined in 32. And this numerical solution, you can see here the dynamical behavior of the system. Now, in order to stabilize the chaotic dynamics of the system, we're going to define a linear control law 35, under which the system will be stabilized. For the proof, we're going to incorporate this linear control law into system 31, which gives us system 35. And this system is equivalent to system 33 after replacing the equation of the system and the expression of the linear control law. Now we're going to choose the diagonal function defined in 37, and we're going to evaluate, or we're going to follow the same steps as the previous demonstration. So we evaluate the difference operator of the diagonal function. We have equality 38 and inequality 39. After replacing the equations of the system along with the equations or the expression of linear control law, we can have this inequality, and since the acceleration function in this case has a Lipschitz constant equal 1, we can have the last inequality, and this means that the variable order, nabla variable order fractional difference of the chosen diagonal function is negative. And also according to the theorem provided in the mathematical background, the dynamic of the suggested chaotic neural network is stabilized under the chosen linear control law. Here you can see the variable order neural network under control. You can see that it tends to 0. And here in this figure shows stabilization of the variable chaotic neural networks 31. To conclude, this work provides a contribution to the topic of the dynamic study of variable order different discrete systems. We describe the type of discrete type variable order neural network using the capital lambda variable order difference operator. Then investigate its asymptotic stability. Furthermore, a chaotic new 3D discrete variable order network is presented, and the chaotic dynamics of the system is then stabilized using a suitable linear control law. For future investigations, we intend to investigate possible application of the standard fractional variable order chaotic neural network, and this application may be used in many fields such as image encryption. Here you can find some references regarding the fractional this variable order discrete calculus, along with some personal contributions. Thank you for your attention.